Hey, so I want to teach a computer to play tic tac toe. And if you've played tic tac toe, then you probably know that if both players play well, then it always ends up being a tie. And what that means is that if we want to teach a computer to play tic tac toe, it has to be able to decide which moves are the good moves that lead to a tie or maybe even a win, and which moves are the bad moves, the moves that will lead to a loss for the computer. So I made a Python program that did this, and it's a pretty cool challenge. So this is the visualization of how that Python program is thinking. So let's say the first player, player A, has moved in the center. Then what the program is going to do, player B, it's going to look at all of the remaining possible moves. And it's going to decide, okay, if I go here, then I think that's going to probably lead to a tie. And if I go here, then I think that's probably going to lead to a loss. So how do we figure out what's going to happen after we make a given move? Well, we do that basically by simulating the rest of the game and estimating that each player is going to take the best moves for them, which makes sense. Now, the tricky thing is visualizing how an algorithm like that would actually work. It might help to visualize the game as a sort of a tree, where the top of the tree is the position where you are now. So maybe that's here, maybe that's here, maybe that's here, and everything under that are the possible moves and positions that the players can end up in. And so what we're going to do to figure out what is the likely result is we're going to look at all of the possible moves under our current position in the tree, so all of the moves for both players, and working from the bottom up, we'll look what is the best move for each player at a given time. So now let's have a look at the code. So here's the Jupyter notebook that I'm working in, and I'll put a link to this in the description of the video. But if you scroll through this notebook, you'll see a few different sections. At the beginning, I have some definitions. I've just defined the players to be equal to either 1 or -1, and that's just for convenience when we're doing a little bit of math here. And the same thing with the outcomes. So I've defined win as 1, tie as 0, and lose as -1. And that allows us to just take the maximum possible outcome, and we get the best outcome for the given player. Underneath this is just a bit of code to display the board, so that's not too important right now. And then after this, we have a bunch of utility code, which is basically used for manipulating the board, checking which pieces are empty, adding pieces to the board, and checking if there are 3 pieces in a row. Now, this is all stuff that if you're a beginner in Python, you'll probably figure out how to do on your own. However, the tricky part for me was to make this function which can actually predict the outcome of the game. And this was the fun part. So I want to show how this part works. And really, it just comes down to this one line here at the end. But it's a whole function. And what that function does is it takes a board, and a board kind of looks like this, which is a list of lists defining which moves have been played already. And then it takes the player, and we need to know which player's turn it is. So the algorithm to decide what the outcome of the game is based on a given set of pieces on the board is like this. We want to check if a winning move has been played. Okay. We want to check if the game is already tied. And if so, we just return win or we return tie. But if neither of those situations has occurred, then we need to do a search. And anytime that we're searching a tree, it kind of makes sense to use recursive code, which means this function is going to end up calling itself. So what it's going to do is it's going to check all of the possible moves for the next player. And remember how player was either 1 or -1? Well, then we can get the next player just by taking the negative of the last player. So it's going to get all of the possible moves for the next player to play, meaning all of the empty pieces, and then it's going to create boards by putting the next player's piece in each of the empty spaces of the current board. So then we have this list of all of the next possible boards that could occur after the current board that we have now. And then for each of those, it's going to predict the outcome by calling this same function again on the new board that was just generated. And that's called recursive function calling, because here the function is calling itself. We're also going to take the negative of the last player because we want to predict the outcome here for the next player. For each of those possible next moves that could be played, we're going to predict the outcome of the game for the next player to go. And then of all of those moves that the next player could play, we're going to take the maximum, therefore the best move that the next player could play. So basically what we're saying is, if no one has won or tied in this current board's position, check what's the best move for the next player. Simulate all of the next moves for the next player and assume that the next player is going to do the best move for them. And then we take the maximum result of those moves, meaning if the next player can win at best, then that's going to be a win. If it can tie at best, then that's going to take a tie. Then we take the negative of that. And so that means that if the best move for the next player is a win, then that's a lose for us. If the best move for the next player is a tie, then that's also a tie for us. So that's what this negative sign does here. And then this outcomes just converts that number, which was created by the max function, back into an outcome, which you'll see is defined here. That's just a little bit of syntax to make everything look pretty in Python. So in summary, what we have here is a recursive function, and it's pretty fun. And what it ends up doing is searching the whole tree of possible tic-tac-toe moves and taking the best move for each player at each given time. And it does that by working its way down to the bottom, comparing the wins and the ties and the losses, and always taking the best one for each player, working its way back up to where we are. And the rest of the code here, well, what it does is it just does that same thing, but it does it for each of the white squares in a grid so that we can make this cool colored map. And so here are a few more examples. If A has gone here, B has gone here, and then A has gone here, then the best move for B is probably going to be one of the corners. Here's another example. If A has gone here and then B has gone here, then actually player A has a lot of great moves where they can win. And then here's one more example. If B has gone here, A's gone here, and B's gone here, then A had better go one of these yellow squares. So if we want to make an AI that can play tic-tac-toe, all we have to do is generate this heat map internally every time the user has played a move, and then choose the green squares if possible, otherwise the yellow squares if there are no green squares. And that's how you make an AI that can be unbeatable in tic-tac-toe.